Alright, so let's get started. Today is the last lecture before the midterm that we cover any new contents. So basically, next lecture on Thursday will be a review session, and we will quickly go over everything we covered before midterm, and I will hold a Q&A session for the homework written assignments questions. If you don't have any. And also I will talk about the general some format stuff about the midterm, so give you a little bit hint about how to prepare for the midterm. Okay. One more thing. So on Wednesday, the office hour now moves to 3 to 4:30. So I hope it won't inconvenient to you a lot. This is due to some schedule change of the TA, so we have to move the Wednesday's office hour to that time. Sorry about that. Okay. So let's continue here. So in the last lecture, we discussed the three kind of hash index. The static hashing, which is the simplest one, it is basically the same thing as the hash table or hash map used in general programming language. And we also talked about two dynamic hash indexes. One is called extendable hashing, where you basically double your space whenever you have an overflow of some buckets. And we also discussed about linear hashing, which improves the extendable hashing in the sense that it will not grow your directory too large. Like if you have an overflow at one bucket for many times, linear hashing will guarantee that you will not increase the size of your directory to exponential in terms of the number of users. Okay. So then the only thing that's left is that we talk about how to use those how to design those hash indexes. But that's based on we have a hash function, right? So how do we actually design a good hash function? This is a key problem in database because for anything to be practical, for the hash table to be usable for practical purpose, you need to have a general good hash function for a wide variety of data types. So here we will discuss how do we formally define a hash function and what is a good hash function. And to simplify things a little bit, we will basically formalize the problem as we have a universe of n elements. So just a reminder, this n notation here is basically a set of numbers. Sorry, it's right here. So basically that's this. Okay. So a square bracket with an n in it means a set of integers from 0 to n minus 1. Okay. There are n possible distinct values in this set. And this is called a universe. And a hash function, h, is basically a function from u to some space of n. Okay? So basically, a hash function will map any of these elements in this in this universe to a number in from 0 to n minus 1. Okay? So to design a good hash function, the thing that we want is that for any set, notice that this is a fixed set. Okay? So even if this is a fixed set, you need to be able to, the most important thing is basically querying X. So for any subset of this universe S, you need to be able to efficiently query one of the elements, whether it's in the set or not. Okay? And so if this set is not fixed, then you have two additional operations where you could have add and delete. Okay, you can add some element to this S. You can also delete some element from this S. And first, we need to basically efficiently do these two modification ops efficiently, and also after the modification to the set S, you will still need to efficiently query any element there, right? So suppose you have a set and you add a bunch of elements into that, you still need to be able to efficiently query for like a particular X, whether that's in the set S or not, right? Okay. So even if we just consider the static case where we have a fixed S, since we do not know the S beforehand, so actually our hash function needs to work for in a general case. Like, so if you design a particular H, a hash function for a particular S set, say this S set is basically all of say even numbers, okay, and you design a particular hash function to support these operations like add, query, and delete. Your adversary can basically pick another set, right? So suppose your hash function is basically, you know S is all the even numbers, and you hash every number to x divided by 2, okay? Let's take floor here. And then some adversary pick another set with the same amount of elements. That's still n over 2, okay? But here we basically we pick all the elements in from 0 to n over 2 instead of all even numbers. Okay. Okay. Then initially your hash is perfect. That's each bucket only has one element in S. Okay. But then an adversary pick the set of 0 to n over 2. Then each of the bucket now has 2 elements, right? So that's not something So if some adversary picks some word set, like if you have, so this is just to say if you have a fixed hash function, and an adversary can typically pick a word set such that the average length of your bucket gets longer. Okay, so to achieve that, basically we need to consider all the n over n possible choices of this S set. Okay, for the hash function to be good. Okay, so unfortunately, so basically, we know for a hash function, if we have a collision happens when two different elements, where x not equal to y, and their hash values are basically the same. Then you know when you do a hash table, when you implement a hash table, these two different elements are going to be hashed into the same bucket, right? And when you do a search for this element, basically you need to scan over everything in that bucket, right? So what we want is actually we want the length of a particular list of some bucket. Okay, so this AHX is one of the list of elements of one of the bucket. Okay, you want the length of this list to be as small as possible, and you want that to have a reasonable bound. Okay, so unfortunately, that's actually a very contradictory goal in the design of hash function, because ideally we can basically make the size of your the range of your hash function n to be in the order of n, right? So in the best case, if you have n elements and you have exactly n buckets, and you happen to design a hash function that maps one element to one bucket, okay? One bucket and only has one element, then it's perfect. The length of each of the lists is basically 1, so then you have a constant cost in this, if you search for something, right? So, however, that's too expensive for our purpose. That might be too expensive for our purpose, okay? Because, so if you have such a large range, like if you have many, so suppose your range is all the integers, valid integers of a 4-byte int, okay? Then your range is going to be 2 to the power of 31, and 2 to the power of 31, right? And so if you have a hash function that maps each of this number to a range of 0 to 2 to the power of 31 minus 1, it's too big to be practical, right? You cannot create that many buckets so that they all fit in memory. So typically we will need maybe a smaller hash range for that. And also, still we want a constant number of elements in each of these buckets. Okay? So when we do analysis, because a hash function, if you have a hash function and you have a bunch of elements from your universe, it's sometimes you can perceive that as a random function. Okay? Although it's not truly random. So since it's random, this number typically is expectation rather than the worst case analysis. Okay, so if you have a hash function, maybe your worst case is really bad. But as long as you have a high probability, so that the maximum length of your buckets are small enough and they are basically constant, then it's good. Okay, if in practice, if you find out, so because the probability is so high, it's not likely you would find some bad hash function for the data set. But if you do, you can just choose another one, right? So that introduces something called a family of hash functions. So basically, for this to work, you have to define a family of hash functions. A family is some way to say to say a set of hash functions. Okay, you can also think of this as a set of functions. Although, so for hash functions, it is this family H is definitely a set, okay? But for a more general case, if you say a family in a mathematical sense, it's not necessarily a set. It could be a class, okay? It could be a proper class. So that's all of the scope. Basically, here you can think of this H as a set of hash functions. Basically, you have a set. You have H1, H2, and so on. Okay? Maybe some finite set or infinite set. Okay? Typically, it's a finite set. Okay? Then what you do is that you basically randomly choose one of these hash functions when you do this when you create a hash table. Suppose I choose this one. Then when I insert things into this hash table, I basically just use this H2 for the hash. Okay, I apply H2 to every element you insert into the table, and for every query you are issuing against the table, and then through that you get a hash value, and you use that as a hash value to check against the hash table. So the same here, because we are basically randomly choosing this H, right? Typically it's uniform. That's to say we have equal probability to choose each of this. Then we can calculate the probability of if you have two different elements. What's the probability of choosing one hash function such that it makes the two different elements collide in hash value? Okay, that means they have the same hash value. So we want this probability to be small. Okay, why is that? Because if this is small, we can prove that the expectation of the length here is really small. Okay, it's a constant in certain cases. Okay, so let's see an example here. Okay, so we've already talked about this in the last lecture about the Pidgeon's code principle, but I'll come back later a little bit. Okay. So basically, let's define a family of hash functions as like this. So this is called universal hashing. So the universal hashing specifies that if your family of hash functions satisfy this probability for every pair of different elements in S, if the probability of choosing a hash function such that the hash value of these two different elements are the same, if that probability is smaller than or equal to 1 over n. Remember, this m here is the range of your hash function. That's basically your hash function are from u to n. Okay, that's the hash function. So basically, you have less than like 1 over the number of buckets you have. If that probability is smaller than that, we can basically guarantee if we have n elements, there is at most n over n. The expected number of collisions between x and other elements is at most n over n. Okay. So to prove that, basically you need to first know a couple of things. So let's do the proof here. The techniques used here is something called the indicator variable. So if you have a random event, which is here the event itself is basically if you have x not equal to y and hx equal to hy, right? So you create something called the indicator variable. Something called an indicator variable, like x. I'll use cxy. Cxy equal to 1 if for this pair of different elements, if the hash function you pick makes the hash value are the same, okay? And cxy is 0 if the hash value are different. Something like that. Then, if we add everything other than x up, That's to say you add all the indicator variables up for every different y than x in S. Okay? And then this gives us Cx. Cx is basically, if you think about that, that's basically the number of collisions given a hash function, right? So because everyone, so if they have y has a collision with x, then Cxy is going to be 1. So you add those ones up, you get the number of collisions you have with x, right? So the thing we want to compute here is the expectation of Cx, right? So the expectation of Cx, you can plug in the formula here. Basically, it's summing up everything that's different than x and Cx, right? And then, because of the linearity of expectation, you can pull the sum out of the expectation. Okay. So this is because of the linearity of expectation. Then what is ECX like? Okay. Remember we have this. If you have two different elements, and for a universal hash family, the probability that you choose a hash function that makes the two different elements hash to the same hash value, the probability is smaller than or equal to 1 over n, right? So you plug in that, that's basically it's smaller than summation over y not x and 1 over n, okay? And how many elements do we have for for y that's not equal to x? That's going to be n minus 1, right? And this is smaller than n over n, right? So that concludes the proof. Okay, so here we prove that. So if you have a universal hash function used in a hash table, the probability, the expectation of number of collisions with a particular element x is no larger than n over n. Okay, and if you think about that, so if you have just a deterministic hash function, as we talked before, so if your if you have a set, you have a universe set here U, and the size of U is greater than or equal to n minus 1 times n plus 1. Then by the pigeonhole principle, we know that there is at least one set, so that you have n collisions. Okay. Okay. So for any deterministic function, you know there's a very bad case for that, right? So if you use a universal hash function, then the argument here would be, so basically, if you do that, the number of collisions with a particular element is not going to be too large. Okay, it's going to be bounded by this one, and this is actually just wondering, is it really smaller than that, right? So let's try to plug that in. So if your U is exactly, that's right. So if your greater n, which is the size of U, is exactly n minus 1 n plus 1, then what is n over n? Okay, and n over n is going to be minus 1 plus n, right? N minus 1. So this is going to be, so in expectation, this is going to be at least no worse than the worst case. Okay. So basically, you are not going to end up with too many.
Plus 1 by
Sorry?
1 by plus 1 by n.
Yeah, that's okay. That's a very small number, so you just ignore that. Okay. So that's fine. You can even just do a round up. Then since n is not too small, not too large, so it's okay. So basically, your expectation is going to be a little bit smaller than the worst case. Yeah. Okay.
So what is the meaning of this number, n minus 1 times n plus 1?
Sorry?
So what is the significance of these numbers?
This number? Okay, this is from the statement of Pigeon's principle. Okay?
Yeah.
Basically that says if you have n hosts, or n plus 1 hosts, and you have n pigeons,
N pigeons and N plus 1. N plus 1 pigeons.
then you have 2 pigeons in one hole, right?
You mean N holes and N plus 1 pigeons?
Right. N plus 1 holes? Oh, sorry. Yeah, sorry. N holes and n plus 1 pigeons, you have at least 2 pigeons in one hole. And you have, if you have 2 n holes and 2 n plus 1, I'm sorry. It's still n holes and 2 n plus 1 pigeons. Then you have at least 3 pigeons in one hole, right? This is easy to see because on average you will have more than 2. So the average of that will be more than 2, right? So the maximum element must be at least that, the average. So that's going to be 3. So in general case, if you have this is something like I should write n here. It's easier. I should write n here. So you have n minus 1, n plus 1 pigeons. Then you are going to have at least n pigeons in one hole, right? So this is basically the same thing as here. So basically everything in U are the pigeons, and the buckets are the holes. You have n buckets and that many pigeons, so that you will have at least n pigeons in one hole. Okay, so this is to say basically this is very bad for deterministic function, because even if it's particular designed for a particular function, a particular universe, and it works for some of the set, you can always find some other set that makes your chain to be too long. Okay, and your chain, the length of your chain is going to be very long. Okay, and in the worst case, of course, so even if you pick any hash function,
But so a question. So but we are not choosing all pigeons, right, at any given point of time.
not necessary. So basically here the pigeons are the S set. S set is a subset of U. Okay. So basically what you are dealing with, the pigeons are everything in this S set. Okay. But if your universe size is greater than, oh I see, yeah. That's what I'm saying. Right. This is not right. So this is basically saying if your size of universe is too large. Okay. Even if your S set could be small. Okay. If your S set is basically if you only have n elements, but your universe size is larger than this, then you are going to end up with many like elements in one bucket, right? But if this n is much smaller than your universe size, right? Then using universal hashing, you basically one chain could not exceed like n over n, right? Instead of n over n. Okay. Right. That's correct. That's why it's confusing. Sorry about the confusion here. So one example of that. Let's give you one like intuitive example. One example for that is basically your universe is basically everything in the in a int. Okay. Everything in int. That's 2 to the power of 31. Okay. And then your S set is a subset of this U, but the size of S is only like 5 elements. Okay? So if your M is something like 10, right? So if your universe, since your universe is basically 2 to the power of 31 divided by 10 times 10 plus 1, something like that, right? Roughly. Okay. So because of that, you're gonna end up with you can always find the S such that the size of this S is going to make one of your chain to be at least 2 to the 31 divided by 10 plus 1, right? Something like that. But of course, this is exaggerated because actually your S only have 5 elements. You cannot have that long, right? But if you think about that, that's basically to say everything, you can always find a set such that everything in one S is going to be hashed to the same number, right?
So the max is then still the size of S.
Right. Right. So you can take a max of that. If this S is like moderately small, then it's going to be like everything is going to be, in the worst case, everything is going to be in the same number, right? But if you use a universal hash family, basically you randomly pick one of the functions from this family, right? And then you know that in expectation you will not have more than 5 divided by 10 elements in one chain. Okay, that's basically less than 1. Okay, so in expectation you are gonna with high probability you know your number of elements in each of your bucket is gonna be only 1.
So here you're randomly choosing S,
No,
the hash function, right?
no, actually not. So S is S here. S is given input. You can think of that as a fixed thing. Okay, but then the thing that's random is the hash function. Okay, so given an input S, I want to find what's the probability of I have a collision that's caused by my choice of hash function instead of the S. Okay, S is given. Okay. But the argument here is in another perspective of this. It's not concerned. We are not actually concerned about like how you choose. Like if you're a user, you do not care about how I choose the hash function. Right? The only thing you care about is that can you, whenever I give you an S as input, can you give me a reasonable hash table that has a constant maximum length of your bucket, right? So here, because you are making this random choice of hash value, the argument is that you expect there will not be too many elements in one particular bucket. Okay, and this number is going to be n over m, or in this case 5 over 10. Okay, and since you have this e, right? So by a simple argument of Markov inequality. So since you know E C of x is n over m, right? And by Markov inequality, we know that Cx that's greater than say c, say a smaller constant c times n over m. It's gonna be smaller than or equal to the expectation divided by this number, right? And it's gonna be smaller than it's going to be 1 over c. Okay, sorry, this is so basically it's going to be 1 over c, right? So since you have an expectation of only n over m in one particular bucket, you know that the number of elements in that bucket is not going to be exceeding this expectation by too much because of this argument of Markov. And this is with high probability, right? Okay, so any more questions about the proofs here? Or the argument here? Okay, so Markov inequality is so I will write it down, write down everything I used here. So Markov inequality it's basically saying if you have a random variable x that is greater than or equal to 0, always greater than or equal to 0, and you know the expectation of this particular x exists, okay, so that's some constant c, okay, of course this c is greater than 0. And what Markov inequality says is that the probability of x greater than some number a is smaller than or equal to the expectation divided by okay. This is the Markov inequality. Okay. So in the previous argument, basically you find that the number of collision with x is going to be smaller than or equal to n over n, right? So that's to say, if you take a look at if you try to find the probability of Cx to be greater than like some constant C times n over m, and this probability is going to be smaller than or equal to n over n divided by C times n over m, and this is 1 over C. Okay, so if you set this C say to 10, okay, if you set that to 10, then this is going to be 1 over 10. Okay, so that's to say if you know this is this number of elements in the expected number of elements in one particular bucket is not too large, then I know with a very high probability, that's 9 over 10 probability, that the actual number of collisions in this particular bucket is not going to exceed 10 times that expectation. Okay, and this is totally accepted. That's the argument here. Of course, the Markov inequality is not the best thing you can you can claim here, because there are some stronger inequalities like Shevchev or Shanov bound or Hopting bound, something like that. But that actually depends on what is the distribution of your hash functions. Okay, so that's a little bit different, because here we are only saying we have a universal hash function, which is very general family of hash functions. It's not very specific, so we cannot make further arguments about how good this is. But even with that, you still can bound the number of collisions in one particular bucket with very high probability. Okay, so that's the argument. So does that answer the question? Yeah, so this is the property of the universal hashing. So since we know the universal hashing is actually good for the purpose of building a hash table, let's consider how we actually construct the universal hashing. Of course, I think the technique here is not really practical, because we are basically assuming this U is a consecutive range from 0 to 2 to the power of U 2 to the power of U minus 1, right? So basically, you are only considering consecutive positive integers from 0, okay? So if you interject, like the construction here we show is only for hash function that maps 2 to the power of U to some 2 to the power of n, something like that. So if you have a more general universe, like suppose you have a universe that consists of a bunch of strings, like A, B, ABC, something like that, and you want to map that, and also this U also have a size of 2 to the power of U, okay? And if you want to apply the construction here, you need to first map these strings into those consecutive integers, positive integers from 0, okay? So that's an additional step we will not talk about here. So here we basically, if you already have done the mapping and you have a consecutive range of non-negative integers from 0, then we will show you how you can actually construct a universal hashing in a very space efficient way. Okay. So the way we do that is basically you take a matrix A. Oh, sorry, I should fill in this first. So basically, if your range is U equal to 2 to the power of U, then for every x in this set, you know x can be written as U-digit binary number. Okay, it's going to be x1, x2, x3, u. Okay, something like that. So one example is, say this u is 2, then you know u is basically 0, 1, 2, 3. And 0 can be written as 0, 0 in binary. 1 can be written as 0, 1 in binary. 2 can be written as 1, 0 in binary. And 3 can be written as 1, 1 in binary. Something like that. Okay. So for this particular U, you can write each element in that in the universe as U digit binary number. Okay. And then what we do, this also applies to the range. So basically, M is, the range is going to be 2 to the power of M. So for any value, say h of x in that, hx can also be written as binary number. Say that's x prime 1, x prime 2, and so on. Right? So everything there can also be written as a binary number. So what we do to construct a universal hashing is we use a matrix A, and it's filled with random bits. Basically, you have probability of 1 over 2 to fill one entry in this matrix as 1, and the other half of the probability to filling that entry with 0. Okay, and then we view this particular number x here, each element in U x here as a vector of 0 1s. Okay, and also the same thing applies to the hash value. So it's basically a vector of 0 1s of length n. Okay, and the arithmetic we do here is on the modular 2. Okay, so whenever you do something like if you do a times b, you are actually doing a times b mod 2 instead of just using the number itself. Okay. So the example. So the example is shown here. Okay. So basically, you have this a function. A matrix. This is A. This is A here, and A are filled with these random bits. And this is an X, and you time you multiply A and X to get the hash value H of X. Okay, and so ideally you want some randomness, but in a hash function it is really not, because for a hash function you need to deterministically map one element to a hash value. Okay, not random. So in this construction, actually, you will find that any whatever a hash function you pick, if you hash 0, it's going to be mapped to 0. Okay, so the 0 element is always mapped to 0. Okay, so that basically means your hash value is not a random function. But here, I'll just remind you of this again. The random choices here is not the numbers in U, rather it's the random choice of H, okay, of the hash function. Yeah.
Shouldn't the hx be of the same size as x?
No, it can be different, because for a hash function, it's basically a mapping from an original range to a new range, right? The new range can have a much smaller space than that. That's the key point of hash function. Right? So they will have different lengths. Okay. So in the example here, you see this is basically x. X is basically 2 to the power of 4, and U is this 2 to the power of 4, and M is the range itself is 2 to the power of smaller n. Okay, and this is the smaller n is going to be 3. So you have a matrix of size 3 times 4 here. Okay. And if you do the multiplication, how do you do that? Basically, that's to get the very first bit of this number. So this number is going to be, this x is actually, this is 8 plus 2. X is 10. Okay? And if you write that as a binary, that's 1010. Okay? And what you do to get the hash value is you multiply this h with x, That's to get the first, the highest bit of hx, you do 1 times 1 here, right? And plus 0 times 0 plus this 2, right? Plus this 2 times value. 0 times 1 and this 2 times value plus 0 times 0. And finally, you do a modulo of 2. That's under the modulo of 2, okay? And this gives you 1 here, over here, right? So if you do this again, like for the second one, it's going to be 0 times 1 is 0, 0, 1. So you end up with another 1, right? And the third example here, you are basically, for the third digit here, it's going to be 1 times 1 plus 1 times 0 plus 1 times 1 plus 0 times 0. And you take the modulo of 2. And notice that this is the first part of this equation is 2, actually 2. So 2 modulo 2 is going to be 0. Okay, so that explains why the last digit is 0. So finally, you know this h of x is 1, 1, 0 in binary. And if you translate that to a decimal number, it's going to be 4 plus 2. That's going to be 6. Right? This is how you use this matrix. Okay? Sorry, how to use this matrix as a hash function. So far, so good. Okay. So the next thing to prove that this is actually a construction of a universal hashing. Okay. So the thing that we need to prove that is that so basically our space of hash functions is all the random matrices A that has random bits in each of these entries. And the size of this matrix is u times n. So you have in total 2 to the power of un hash functions in this hash family. And then you need to prove. Our goal is to prove that for any x, y in 2 to the power of u and x it does not equal to y, we need to prove that the probability of choosing one hash function such as h of x equal to h of y is smaller than or equal to 1 over n here. M is basically 2 to the power of smaller n, right? Okay, so that's our goal. This is the thing we need to prove. Okay, so I'll go through proof. It's a fresh page here. This is already on Canvas, so if you need to review this material, you can take a look at the slide. But here I will start from the initial, with an empty slide, just to go through the pieces. Okay. So the way we see this is that, remember, here we have a matrix X. Matrix A, and A is has a size of n times n. Okay, so basically you can view that as a bunch of vectors. So basically this is oh sorry, it's not n, it's u times n. U times n. It's actually n times u. Yeah, I think here's a mistake. This is n times u, right? You write the rows first, then the columns. Okay. So this is a matrix of. So this is A is a matrix of size n times u, and so basically you have n rows here and u columns here. And you can actually view that as a bunch of vectors. So you can write that as a vector. You can write that as a bunch of vectors. Let's denote these vectors as C1, C2, and so until Cn. Okay, you have n vectors. So then this AUN can be expressed as a vector like this. That's C1, C2, and C. Okay, and then each of these vector has a size of, so each Ci here has a size of u times 1. Okay, it's a vertical vector. Then the x, once you times a and x can be viewed as u different digits. Okay, so you have x1, x2, and until xu. Okay, so basically each xi here is a 0, 1 digit. Okay, and as the result, what's the result? The result is going to be a vector that's called h of x. H of x is going to be a vector of size n times 1. Okay, there are n rows and 1 column. It's a vertical vector. And since you express the A as a bunch of vectors, so the final result can actually be expressed as x1 times c1 plus x2 times c2 plus xu times cu. Okay, something like that. Right. Something doesn't match here. So
Yeah, these are columns.
yeah, u rows and columns, m rows and columns. Right. I'm wrong. Yes, I'm sorry. Something got mixed up. It's m rows and u columns. Right. And this is actually u here. Right. Yes. So you basically add everything up. I'm sorry. This should be u columns. Okay. And then, since you have expressed that as this, let's say we have two different elements from U. So basically we have x1 doesn't equal to x2. Okay, so the subscript, sorry, this is not a subscript. It's a superscript. The superscript actually means different vectors or different elements in U. Okay. And if you put a subscript, that means different different digits of this element in U. Okay. So basically, x1 is going to be a number in U, and x1 is going to be the first digit of this x1 element. So if you have two different elements in U, and we know that there is at least one digit that's different. Okay, let's say this. So without loss of generality, let's say that digit is 1. So let's assume x1 is not equal to x2. X1 2. Something like that. Okay, and then since these are different, you only have two choices, right? You only have two choices. Either x11 is 0 and x12 is 1, or x11 is 1 and x12 is 0. It doesn't matter. They're basically, in the problem, they are symmetric. So basically, you can assume one of them, right? We can also assume x11 is 0 and x12 is 1. Okay, that's an assumption, and it doesn't change all the proofs we do here. If you do that, let's see what happens with this vector. So then, if you take a hash function of h1, you take a hash function of x1 here, you end up with, since x11 is 0, so this term disappears in the final result. So you get a bunch of summation of I from 2 to u, xi, ci. So that's the result of, that's the hash value of x1, right? And if you take a hash value of x2, you get, this. I should write is a C1 because x12 is actually 1, so this term becomes just C1, okay? And plus whatever you have in the latter part, okay? I equal to 2, I from 2 to u x I2 times ci. Okay? Alright. So the next thing that happens is that if you look at this, so let's just look at the second part of this. Let's first ignore the first thing. Okay? So basically the second part of these two formulas is going to be, so this is h of x1. It's going to be some combination of 0, 1s. Okay? Something like that. It's going to be some combination of 0, 1s. And h of x2 minus c1, that's the second part of that. It's going to be some other combination. It's going to be some other combination. It's not like the same one. Let's assume it's like this. Alright. Okay, so suppose it's 1, 0, 0, 0. Okay, something like that. It's just different. No, sorry. It can be different or the same thing, right? Then what happens is that h of x2 is actually c1 plus. Sorry, c1 plus that is actually h x of 2, right? So this is gonna end up with something like 0, 0, 0, 0. Let's put a 1 here, something like that, right? It's just anything. I just write anything here. But the key point here, the key observation here is that there is only one possible C1 of choice, so that the summation of C1 and this vector here is exactly the same as h of x1. Okay. So why is that? Why is that? So first, let's prove there is one. Okay, there will be some vector that does this. Okay, so the way you construct this C1 is that you see. Let's put it in a new slide. So suppose this is h of x1, and this is h of x2 minus c1, okay? And this is just something like 0, 0, 1, 0. And this is, 0, 1, 0, 1, 0, 0, and 1, 1, 0, 0, 0, okay? And you want to construct some C1 such that the sum of this vector and this vector just equals h of x1, okay? And the way we construct that is basically you just do, like, you can do C1 equal to h of x1 minus h of x2, right? So that's basically, you do, the first one is going to be 0 minus 1 modulo of 2, and that gives you 1. Then this is the same, 1 minus 0 modulo of 2, so the second digit is going to be 1. And the third one is 0 minus 0 modulo of 2, and that's 0. And the same thing goes on the last digit, okay? So this way we can construct one C1 such that the sum of these two vectors exactly equal to h of x1, right? And you know the sum of these two vectors these two vectors here is exactly h of x cubed. So here, up until here, we have proved that we can construct some C1 such that the two different values have the same hash value. Okay, the two different axes have the same hash value under some sort of hash value. So the next thing to prove this is that any other choice of C1 doesn't give you the same hash value. Okay, any other choice of C1 doesn't give you the same hash value. The reason is that, so here, let's say there's another C1. So suppose this is one. Okay. So suppose we have another C1 prime. And C1 doesn't equal to C1 prime. That means basically one of the bits is different. Okay? Let's say just this bit, the third bit. Let's say just the third bit in C1 prime is different from C1. Then you know the result of adding this vector to C1 is going to be different from adding this vector to C1 prime. Okay? Because this is the same. Okay? If you add 0 plus 0, it's going to be 0. And since this digit is different, so the result must be different. Okay? So that means the end result is basically h of x cubed. So some bit in h of x cubed is going to be different from this one plus this one, the h of x cubed minus c1 plus c1. Okay? That is, since the C1 is the one that we construct so that the hash value of h of x2 is the same as h of x1. So that means if you use C1 prime that's different from C1, the hash value of x2 is going to be different from hash value of x1. Make sense? Right? So that means out of how many choices do you have for C1? Remember, the C1 has a size of n times n times 1. Okay, so that basically says you have 2 to the power of n choices of C1, but only one of them is with only one of them is gonna make h of x1 equal to h of x2. Okay, so let's write this down. So basically, the probability of h of x1 equal to h of x2. So since the other things are fixed, so we know the other things are given. Okay, C2, C3, until Cn. Okay, so basically the conditional probability of getting the same hash value by choosing C1, given the other vectors there in A, the probability is going to be exactly 1 over 2 to the power of n, right? And then by the Bayes theorem, okay, you know that the probability of h of x1 equal to h of x2 is going to be the summation of every possible choice of the C2, C3, and Cn, and you times this 1 over 2 to the power of n times the probability that you choose that C2, C3, and Cn. Okay, and then you can use the distribution law to pull out the 1 over 2 to the power of n. Then you know the summation of all the possible choices of C2 until Cn is going to be 1 because of the law of total probability, right? So this is exactly 1 over 2 to the power of n. And that proves the thing worked. Okay? A random choice of this hash function h is going to make your hash values of two different elements to be the same with probability no larger than 1 over n, which is exactly 1 over 2 to the power of small n. Okay? And that's the proof. Yeah, so so far so good about the proofs. Any questions about the proofs? Yeah, so if you still have some questions about that, I suggest you take a look at the formal proof here. Yeah, I think I made a little bit mistake here because this is actually n times u, so I should change this one to cu. Okay. And another thing here is that this is not plus h of x1. It's exactly, it should be plus x2, sorry, x2 of 2 c1 c2 plus until x of n 2 cn, something like that. And I'm missing a superscript here, okay, as well. Sorry, it's just a little bit like mistakes in the notation. Okay, so I will post a fix for this. I'll post a fix for this on Canvas, so don't mind of that. But be careful if you are looking at the old version of the slide. Okay? And also this one should be fixed. This is not u times n, it's n times u instead of u times n. So that's the construction of the universal hash function, universal hash family. So any questions about that part? Okay. Yeah. So I'll just move on. Okay. So given that, so basically, if you have a space, you have a universe, you can construct a universal hash family for that. So another thing to think about is that can we do the hash function perfectly? That's basically you want every lookup to only involve a constant number of lookups. Okay, you want to guarantee that every lookup has a constant number of lookups. Okay, that requires the length of the chains in each of the bucket is deterministically bounded by a constant. Okay, so how can we do that? Of course, we cannot guarantee that for every choice of s. Okay. If you give me any s, as we discussed before, any choice of the deterministic hash function is not going to work. But if you tell me this s in advance for a static case, the best thing that we can do is that we can somehow construct a good hash function. Okay, this is what we are talking about here. This is called perfect hashing for a static input. Okay. And the goal is that you want every bucket to only have a constant number of elements in that. So there's a very naive approach. Let H be a universal hash family, and let the n, this n here is the size of the like your hash table, like how many buckets you have there, or the size of your range of the hash functions. Okay, and you have n elements. Okay, that's to say the size of S is n. Okay, and you let the size of range to be n squared. Okay, then we just pick a random h from the hash family, from this universal hash family. Why this works? Because we claim that if h is universal and you pick the size of range to be n squared, then the probability of so that there is no collision in S is at least 1/2. Okay, so with probability of at least a half, you can find the H that does the work. Okay, that's the perfect hashing. Okay, however, so if you are unlucky, like you throw a dice and it's the other half of the probability space, you do end up with some collision. What you can do is that you can just try again. Okay, you just try again and pick the next one. And since, like say you have k trials, okay, if you have k trials of this, after k trials, the probability that you still end up with something with a collision, the probability of all have collisions after k trials, it's going to be smaller than or equal to 1 over 2 to the power of k. And since as long as we make a reasonable number of trials, this is going to be diminishingly small. Okay? So in practice, this is basically means after a couple of trials, you're definitely going to end up with some hash functions such that there is no collision anywhere. Okay? So the only thing that's remaining is that how can we prove that? How can we prove this claim? Okay? The claim is basically a simple application of the unit bound. Okay? So the unit bound is basically something if you have two events, A and B. Okay? So the probability of A happens and B happens is going to be greater than, so the probability of A happens and B happens is going to be smaller than or equal to the probability of A plus probability of B. Okay? This is very easy to understand. Like if you throw a coin, you flip a coin and see whether it's head or tail, right? And let's say your event A is that you end up with a head, and your event B is end up with with a tail. Then not an N, it's actually O. Sorry about that. Yeah. So either you end up with a head or a tail. So the probability that you either end up with a head and tail is going to be the sum of these two, right? It's exactly. Okay. But what if I say this? So if you throw a dice, right? And the dice has 6 sides. You have equal probability to end up with one of the sides. So suppose the event A is you throw a dice and you end up with numbers 1, 2, 3. And the event B is that you throw dice and you end up with an odd number. Okay? So basically A is number 1, 2, 3, and B is going to be number 1, 3, 5. Okay? So if you do a careful calculation, A or B, the probability of A or B is going to be 1 over 4. 4 over 6. 4 over 6. But it's going to be smaller than or equal to the probability of A plus probability of B. Okay? And this is 1 over 2, and this is 1 over 2. The reason for that, if you do this carefully by the exclusion law or something like that, don't remember, it's A or the probability of A or over B is actually probability of A plus probability of B minus probability of A and B. Okay? So if you do that, you know this is called non-negative. That's why this gives you the probability of either of the happens is the smaller than or equal to the sum of the individual probabilities. Okay. So basically here we just apply this unit bound. Okay. So basically, let's think about how many pairs, distinct pairs we have in an S. If we have n elements, then we have n choose 2 possible pairs. Okay, so this is going to be n times n minus 1 divided by 2. And you know, for each pair, the chance they collide is smaller than or equal to 1 over n. Okay, so the probability that there is even a collision is smaller than or equal to the sum of every pair that has the sum of probability of a particular pair that has a collision. Okay, so since you have this many pairs and each one has this many probability to be collision, then the total the sum of these probabilities is going to be n choose 2 times 1 over n. Okay, and if you do the calculation here by plugging n equal to n squared, you get this probability is smaller than 1 over 2. Okay? Since the probability of there exists some collision is smaller than 1 over 2, the probability that you do not have any collision is greater than or equal to 1 over 2. Right? So that's probability of no collision is greater than or equal to 1 minus that. Okay? And it's 1 over 2. Okay? So that's how you prove this naive approach actually works. But this is not ideal because if you have n elements, say you have 1 million records, and you want to do construct a perfect hash function for that, you would need 1 million square number of buckets. That's absurd, right? So there's actually a better approach. You actually can do this in linear space. The way to do that is actually you use a hierarchy of, two-level hash function. Okay? That's a hierarchy of hash functions. So basically, you first hash all the elements in the table into a bucket size of n. So basically, you hash them into n buckets using a universal hashing. Okay? As we know, this can be constructed so we have, this is just a simple construction. You just pick any one from that universal hash. Okay? Then for each bin, if this bin already only has one element, then you are done, right? So basically you have a bunch of bins or a bunch of buckets. And if one of the bucket only has one element, you're done. You're done with that. Okay? But if you have multiple elements, you do another level of perfect hashing to make it make this bin perfect. So you use a second level of hash function to rehash this buckets inside that bucket. Okay, that's a hash table nested with another hash table. Okay, so basically this buckets in a whole is a first level hash table, and in each bin, if you have more than one element, you're going to create a smaller hash table for that bin. Okay, and then you use perfect hashing as we constructed in the naive approach. Okay, and if you do a careful proof here, it's easy to prove that the space here, the total number of buckets you end up with is going to be smaller than, it's going to be, in expectation, it's going to be linear. Okay. So the thing here is that basically, suppose in the first level of hash, you end up with C1 element in the first bucket, C2 element in the second bucket, and so on, and until you have like n buckets. Okay, and the total number of buckets is going to be summation of C1 squared plus C2 squared, and plus to Cn squared. Okay, and if you carefully compute the expectation of that, this is going to be something in the order of n instead of n squared. Okay, so due to the time limits, I'm sorry, I'm not going to talk about the proof here, but this is basically a simple application of integer variables, and yeah, I think it's basically integer variables and some Markov inequality algorithm. Okay. So that's the better approach for perfect hashing. Yeah. Actually, you are using one hash function for the first level, and potentially n hash functions for each of these buckets in the first level. Right, they are totally independent choices of hash functions from some particular hash parameters.
Sorry to ask a question. So the second level hash table, it's not the same table, it's just a table within the bucket.
Right, it's a table within the bucket. Basically, each of your bucket now becomes a table.
But if that table is n, then don't you guys still have n squared space?
No, actually, this is the claim here. So suppose your bucket size, each of your bucket size is C1, C2 until Cn. Then you know the bucket size. number of buckets in one particular the number of buckets in one particular bucket in the first level is going to be ci squared. Okay, and if you sum those up, it's going to be the total number of buckets, right? And we can prove that the expectation of that is actually OA. And by a Markov inequality, you know that's not going to be exceed multiple times of n by very high. Okay. So that's the better solution for perfect hashing. And I think the times is almost up. Okay. So the last thing is, what if you have a dynamic S? Okay. So if you have a static S, of course you can construct that perfect hashing easily. But if this S is not given ahead of time, or you can have insertion deletion all the time, then those techniques doesn't work at all, right? The perfect hashing doesn't. So then somebody in the early 2000 proposed this cuckoo hashing algorithm. It got the name because of this cuckoo bird. They basically, I think it's either their child of these birds will push other child out of the nest to get space. That's the same thing happens here. Basically, if you each hash value you have two different hash functions, okay? Two, I think, universal hash functions, or sorry, it's not universal, other hash functions, okay? It should be two wise independent hash functions. And so for each of the elements, you will use those two hash functions to get two potential places to put in your hash table. And then if one of those space is empty, you just put that element in that space. Okay? And when you do a lookup, you look up both space to see if that element is there. Okay? And then if both spaces are occupied, then you basically push another one of them to other one. Okay? Because everyone has independent choices of two spaces. It's not likely they're going to climb. So then it's basically like what the cuckoo, baby cuckoo bird do. Okay? They push out other birds. So that's why it's called cuckoo hashing. And it can be proved that this is so basically it's an ON space perfect hashing. Like with high probability, of course. Over time, you need to increase the space of your hash table because it's dynamic. Okay, so I'm gonna end here. So the only thing we're left is K universal or K wise independent hashing. I'll finish this very quickly in the next lecture. Okay, see you next time.